Gradient vector. First off, before we start to do any math, let me just say what the gradient vector is. I'm going to say this a couple of times during the video. It's like the most important concept. Everything that we do or learn about the gradient vector falls out of this fact. The gradient vector is the vector that points in the direction of greatest increase of the function. So, it points in the direction of greatest increase. Take a look at this surface here that we have. And if I think of it as like a valley, a hill, and things that I can walk on, let's look at it from like a bird's eye view, as if we would see it on a map. On a map, we would be looking straight down on it, and we could have any place that we were. Let's say I was standing at this place in this valley. There would be a direction that I would go, there would be a direction that would point me straight up in the most, in the steepest way up. So let's see here. If I was standing at that point, maybe straight up would point me this way. I should go in this direction. Now it's a 2D vector in this 3D shape because it's pointing me a direction on the map. So it's a 2D vector. It's pointing me in the direction on the map. If I was on the top of a hill, the very peak, there would be no direction to go straight up. So the math would give me the direction, the gradient, as a vector of all zeros. What if I was at the bottom of a bowl and then every direction would be, it doesn't matter, go any direction you want, it's the direction up. Then the gradient again would be all zeros. But the gradient vector is the vector that points in the direction of greatest increase in the function, so the height going up. So we're talking about a function. The height is given by a function of x and y. So our direction, our gradient vector then, is a 2D vector because it's a direction that I would walk on the ground to be going the most steepest way up the hill. And our direction then, we write the gradient as this upside down triangle f. This means the gradient of. So the gradient of the function. It's a 2D vector. It's got an xy direction because it's on the ground. And it's defined as, we calculate it as just the two first order partials. The derivative of this function with respect to x, the derivative of this function with respect to y. So it'll be a formula. It'll have x's and y's in it, and if I'm at the point, a certain x, a certain y, I can plug those x's and y's into the formula and get a direction. So it changes, and yeah, that makes sense, right? Depends on where I am standing on the ground. If I'm here, it looks like going off in this direction is the direction of greatest increase. If I'm over here, then going off in this direction looks like it's the direction of greatest increase. So the vector is different for different xy points. It's different for different points on the side of the mountain, let's say. So we get a direction out of this vector, the direction of greatest increase. But a direction has two kinds of information, or sorry, a vector has two types of information to give me. The direction is one, and its magnitude is the other. The magnitude of that gradient is that maximum rate of change. So this vector says go in this particular direction so that you go up the fastest. And its magnitude tells me how fast you go up in that direction. So let's draw some functions here. And we can see them as level curves. If I'm drawing here for level curves, that's what these lines are here, right? This is our function. But notice this line here, that's all the places where z is equal to 0. That's the level curve. So this is a level curve, z is equal to 0. Let's take a snip of this and we can draw on it. So what I'm saying is this continue that. That's the level curve when I set z is equal to 0. So here z is some function of x and y. I'm taking these level curves. This one will be the level curve when I set z is equal to 1. And this one follow that level curve, okay, would be like the z is equal to 2 part. So they're level curves. They're slices at different heights. Now, if I were to, we're talking about walking about paths on this mountain, and we've already sort of defined, I've already said that if I take the gradient of that function, I get some xy, well, I get derivative of f with respect to x derivative. I get this vector says point in the direction of greatest increase. So if this is the vector that's the greatest increase, then greatest decrease must be like negative that vector, right? If this way is straight up the hill, then this way is straight down the hill. What about if I walk along this level curve? Well, if I walk along this level curve on the side of the mountain, this one is, well, let's walk on this one. If I'm walking on this one, then my height doesn't change. I'm following this path on the mountain. The height is always 0. So it's neither an increase nor a decrease. I'm not going up or going down. So that's going to be my argument here, that if, let's say I'm at this point, if I go wow, that's not a good color to pick there, is it? If I go this way, that's on the level curve or on the level curve. So that's no increase, no decrease. If I go this way, that's perpendicular to the level curve. So that's the greatest increase. Anything that isn't perpendicular has a little bit of a component in the level curve. Is me walking a little bit along the level curve. So the gradient needs to be perpendicular to that level curve. Let's do some math that sort of shows that. But right now my picture, I'm trying to indicate that the gradient should be perpendicular to these level curves. So to see that, and we sketch some curves, level curves, contour lines. That's what these contour lines here are, level curves. Contour lines is more of a map, a topographical map term. Level curves is more of a multivariable calculus term, but they mean the same. You're connecting all the points together that have the same height. In this case, a height of 0. All right. On that curve, the z, the height is the same. So all level curves have the equation f of xy is equal to c for some constant. The one we drew here is c is equal to 0. That's the, oh, I got the weird color. That's the f of xy is equal to 0. But this one is f of xy is equal to 1. They're all f of xy is equal to some constant. What if I differentiate this function? Now, before I differentiate that, I'm thinking about me walking on this level path, walking on this mountain. So my x component, like longitude and latitude, it's a function of time. My y component, it's also a function of time as I wander all over this mountain. If that means when I differentiate this, I'm going to use the chain rule stuff that we learned. So it would be derivative of the function with respect to x times x prime plus chain rule. Derivative of that function with respect to y times y prime. And now I'm differentiating that constant of 0, or sorry, that constant of c its derivative is 0. So here's what I get then. Now this is just saying take the level curve, differentiate the level curve, thinking of the x and the y as functions of a parameter. I think of it as time because I'm walking around the mountain surface. Now let's take a look at this expression. I can write it as a dot product. I can write it as the vector fx, fy, dot product with the vector x prime, y prime equals 0. But this is just the gradient. So the gradient is perpendicular to, what's this vector x prime, y prime? That, go a couple of videos back, this is our tangent vector to the level curve. That's this piece here. That's our tangent vector to the level curve. And this gradient then, this algebraically shows that the gradient is perpendicular to the tangent vector. We argued it out here with our story about walking on the mountain, and a level curve is neither increasing nor decreasing, so I want to be perpendicular to that, but to be the gradient. But this algebraically shows it. So what does that mean for us? Well, let's catch up here. We parameterize the curve and then we differentiate it. So algebraically, we've showed that the gradient of the function, as defined by those two partial derivatives, is perpendicular to the tangent vector to that level curve. So I'm going to write that as x prime and y prime. That's what we've shown. So again, this is all sort of wrapping around. The very first thing I said was the gradient's the vector that points in the direction of greatest increase. And all we've done so far is kind of indicate that that's true. Proved it's true here algebraically, drew it and argued out why it should be true geometrically. And we talked about the magnitude of that vector being that rate of change. So the magnitude of that vector is how fast what the maximum rate of change is. So the gradient's a vector. Its direction says the direction of greatest increase. Its magnitude says what is that greatest increase. Now, what if I'm not moving in the exact gradient direction? Because right now from my picture, I've got like two directions. Here I am on this point. If I take the gradient, I'm going straight up the mountain. If I take the tangent vector to that level curve, I'm neither going up nor going down because I'm walking along that level curve. And we had over here, if I go negative the gradient, then I'm going straight down the mountain at a maximum rate of decrease. Okay, what if I'm going in some other direction? So since we got arrows all over the place here, let me put myself over here. So here I am. There's the level curve. I know that this direction, perpendicular to the level curve, I'm going to draw it out here so I can see it. I know that's the gradient. I know that this is the tangent vector to the level curve that's perpendicular. What if I'm walking at, I got to get a color that I can see. What if I'm walking at, I don't know, some other direction, like this? So now I'm walking a little bit up, but not the maximum value of up. Maximum value of up would be on the gradient. This would be, the blue would be level curve, tangent vector to that level curve slice, that contour line. That would be no increase. So I'm walking a little bit of both. So how fast am I going up? I know the direction. I picked the direction. I just want to know how fast up the hill I'm going. That's what our directional derivative gives us. So the directional derivative is going to be a number, and it's a measure of how fast the height is increasing in the direction that I choose, AB. So it's a dot product, right? Go back to it makes sense that it's a dot product between where I'm going and the maximum rate that I could be going up. So I want to know, it's almost like a projection, I guess. How much of this direction is straight up? I want to know the component of this on the pink, my direction on the greatest, on the increased direction. Now, how do we get this? Well, I'm picking the direction I'm doing. I guess let me go back to this. Let me restate this because I want to make it. I want to clarify that. I want to know how much of this is going up. So I really want to know. I said it unclearly. I want to know how. And my triangle's upside down. What the hell? Gradient's an upside down triangle. Okay. I want to know how much of the straight up the mountain gradient vector, how much of this is in the direction that I'm going. That's what I want to know. So I want to know how much straight up the hill do I have when I go in this direction. Now, if I pick this direction, I pick it with a vector. If I say this vector, or if I say this vector, which I'm trying to draw here is extra long, I don't want my answer to change, because I just want to. I'm picking the direction. I don't want it to be that I give you a longer vector in that same direction and my answer is twice as much. So really, when I give you a direction, I need to make it a unit vector. So that has to place in this. We talk about in the direction of a unit vector. So if the direction that someone gives you is not a unit vector, the first thing you do is make it into a unit vector. So the vector that we're talking about here is a unit vector. AB is a unit vector. Its magnitude is 1. Now we can do directional derivative. The directional derivative is just the dot product of the gradient on that unit vector. How much of that straight up the hill vector is in the direction that I'm going? Now, if the direction that I'm going is in the level curve, say I pick that direction, well, it shouldn't be going up at all. That's why the dot product gives me 0. Sure, the dot product gives me 0. If the direction I choose has an angle bigger, has an angle bigger than 90 degrees from the direction straight up, well, then I guess I'm going a little bit down. So the directional derivative would give me a negative. The dot product would give me a negative value here. So directional derivative, defined as big D directional derivative, in this direction. Remember, this u is a unit vector. We talk about the function evaluated at that point. Because the gradient vector changes for different points, the directional derivative is different for different points. And the answer, the directional derivative, gives me a number. Let's say everything's measured in meters. So x is a meter, y is a meter, z is a meter. The units would be in like meters per meter, which would be take 1 step, 1 meter step in the direction of u, and you would go up, if the directional derivative is positive, up that many meters in the height in the z direction. Let's do an example. So gradient vector that points in the direction of greatest increase, directional derivative is the maximum rate of that increase, of that rate of change. The gradient is perpendicular to level curves. All right, let's look at an example. Think about here this function z is equal to x squared y plus y cubed. There's a picture of it with scientific workplace. It's not that great. Here's a better picture with dp graph. That's what this function looks like. So it looks like there could be a flat spot here. Depending on where we are, the gradient's going to point in the direction of greatest increase. Remember, it's a 2D vector, so it'll be a vector like go northwest or something like that. Um, I guess the first thing is let's find the gradient vector. That's what they're asking us to do. Find the gradient vector, and it says specifically at the point 0, 1, 1. Let's find our gradient vector in general. So the gradient of z, the gradient of f is equal to, it's a vector. First I differentiate the function with respect to x. Now I differentiate the function with respect to y. There's the gradient vector. It's a formula with x's and y's in it here, and we got, all right, find the gradient vector, but now specifically at the point. So here it's like it changes with different x, y values. Oh, when we saw this picture, I said, it kind of looks like a flat spot in the middle. But it's hard to tell from the picture if it's exactly flat or not. If it was flat, then the gradient would be the zero vector. So it looks like when x is equal to 0 and y is equal to 0, it looks like algebraically that gives me the zero vector. So that is a flat spot. Okay, find the gradient at the point. So let's get that. And interpret its meaning. All right, let's find it first. So I'm going to write at, and I'm going to write the point. Now I'm writing the point 0, 1, 1. That 0 is the x value, that 1 is the y value, that 1 is the z value. It doesn't come up in our gradient. In fact, we don't even need to, they didn't even need to give it to us because they gave us the formula. I can see that when x is equal to 0 and y is equal to 1, that z is equal to 1, but it's just been given as a 3D point. So when I plug that in, I get when x is equal to 0 and y is equal to 1. So there's the vector, 0, 3. Interpret its meaning. I've said it a zillion times, right? The gradient is the direction that points in, the gradient is the vector that points in the direction of greatest increase. So 0, 3, so that means don't move in the x direction at all. Go straight up in the y direction, go straight in the y direction. That's the direction of greatest increase. Does that make sense from our picture? So I want to go to when x is equal to 0 and y is equal to 1. So that's about here, right? Because these are x is equal to 1, x is equal to 0, y is equal to 1. So there's y from -2 to 2, so we want to go about halfway in between here. And x is equal to 0, we want to go exactly halfway on this axis. So we're about here. And the direction would be go straight up as fast as you can, just walk in the y direction. Okay? I mean, it kind of makes sense from the I'd be about here, go straight this way. Go straight, let's say if I'm looking straight down here as a topographical map, you'd say, I'd be here, you'd say go north, go directly north. So I'm interpreting its meaning. But it's like north could be 0, 1. What's with the 0, 3? Well, the magnitude of that 0, 3 vector is 3. So that means if you go in that direction, you're standing at the point 0, 1, 0, 0, 1, 1, and you go north, you're going to go up 3 meters for every meter you step forward north. That's the sort of tangent slope. Now, that's the reading right there. I can see that it changes, right? The further I go up north, the steeper the slope should be. Let's look at it this way. The steeper the slope should be, so like the faster the gradient should have a bigger magnitude up here, but it should still point from the picture straight north. From the algebra, yeah, as long as x is equal to 0, the gradient's always going to be 0 something. As the y gets bigger, the magnitude of the gradient gets bigger. So we got the gradient vector and we interpreted its meaning. Is there anything else we can wring out of this? Well, I guess you can say if you had a vector perpendicular to this vector, which would be like 1, 0, anything 0 would be perpendicular to that. That would be walking on the level curve. That would be neither increasing nor decreasing. All right. What's the maximum rate of decrease from that point? Well, 3 is the maximum rate of increase, the magnitude of the gradient. So if I go backwards, like in this southerly direction, you drop down 3. So the maximum rate of decrease would be 3. Now I got to be careful if I'm answering questions, especially like on an automated system. Do they want me to put -3, or is the automated system, the automated homework system, going to say to me, no, the decrease is in the words, the negatives in the word decrease, and we just wanted the answer 3. I got to be careful with how to answer that kind of question. But anyway, if I go south from this point, every step I take in the southerly direction drops me down the hill 3 meters. That's what that's saying. In what direction should I go so that there is no increase? That's on the level curve. That's perpendicular to this gradient. So east or west, doesn't matter, is the level curve at this point. So some 1, 0, 10, 0 vector, something like that. How fast is the z changing in the direction 1, 3? So now I'm not going north and I'm not going east or west or south. It's some other direction. So this is asking about directional derivative. So I'm still at the same point, 0, 1, 0. So I'm still at this point, but I'm going, okay, let's look at it straight up and down so the north and south stuff makes sense. I'm here and I'm going at the point 1, 3. So I'm going off in this direction. If I go off in this direction, it looks like I'm going up the hill. So I expect my directional derivative to be positive. But first thing I got to do is this is not a unit vector. So I got to make this into a unit vector first. So the unit vector that just has the direction in it, I got to take this 1, 3 and divide out its magnitude. The magnitude would be 1 squared plus 3 squared, that's 10, square root of 10 would be its magnitude. Now it's a unit vector that's just giving me purely the direction. And now we want our direction. So to answer this question, how fast is z changing, I want its directional derivative. Let's get our proper notation with this then. So at the point when x is equal to 0 and y is equal to 1, the directional derivative in u, so this is the vector, the unit vector that we're talking about. I'm going to put it down here as its subscript. And we want the gradient of that vector. So the gradient of that vector we already have is 0, 3. And we want our direction vector here. And I'm going to take the dot product. And dot product gives me a number. And I'm getting 9 over root 10. 0 times this, 3 times this. Undo. Undo. This was 3. Okay. Some copy paste acting up. Anyway, I get a number. So if I'm going in this direction, I'm going up at this rate. I knew it was going to be positive. The maximum, this is like, let's get this as an actual number. Well, it's not quite 3. 3 is the fastest I could go up. That was the magnitude of the gradient. So I'm going almost as fast as I could go up the hill. That'll be in like meters per meters. Can I stop here? Oh, of course I can. I will. Let me warn you that the most common error that I see in the gradient section of multivariable calculus is people forgetting that this is supposed to be a unit vector. You see that like 30% of the time. 30% of the time I see that 100% of the time. But my point is, slow down here and be careful that your direction is a pure direction. It's a unit vector. So we've had an example where the gradient vector, the direction that points in the direction of greatest increase of a function, is a two-dimensional vector, like directions like northeast and southwest, that kind of thing. But that's if our function is a 3D function. What about if our function is a 4-dimensional function? So its domain is a 3-dimensional space. In other words, the gradient's going to be a 3-dimensional vector. Our example, again with the fire in the room, don't do this, but let's just say that the density of smoke in a room is given by this function. So here's smoke density. It's given by an x direction, a y direction, and a z direction. So generally smoke rises so that the near the ceiling is supposed to be smoky. You're supposed to stop, drop, and roll or whatever. Anyway, the idea being that different places in the room, different x, y, z points in the room have different smoke densities. If I'm in the middle of the room at the origin, the point 0, 0, 0, where should I run? So here's where knowing some multivariable calculus is going to get you out of some trouble. So where should I run? Well, the gradient's going to give me the vector of greatest increase. So let's get the gradient of the smoke density function. Now it's going to be a 3D. I have to differentiate this function with respect to x first. So that's going to be derivative of the outside, leave the middle alone, multiply by the derivative of what's inside, minus, okay, there is no x in here, so its derivative is 0, minus 1, and there's our first component of the gradient vector. Now I need the partial derivative of this function with respect to y. That's going to be x cos xy. I'm differentiating with respect to y, plus z sine zx, zy, and there's no y's in here. Finally, I need the derivative with respect to, the partial derivative with respect to z. No z's, one z here, so that's going to be sine of zy times the y, because of the chain rule, regular chain rule, minus 0 minus 2z. Okay, there's my gradient vector, but I need this evaluated at the origin. So x equals 0, y equals 0, z equals 0. So when I make y equal to 0, this whole thing disappears. When I make x equal to 0 and z equals 0, this whole thing disappears. And likewise, oh, okay, it simplifies down nicely. So this is the direction, minus 1, 0, 0. That's the direction of greatest increase. So I want to go the other way. I want to go the direction of greatest decrease, so negative the gradient. So 1, 0, 0. Quickly do those calculations and then run in the x direction. And you'll go to where there's less smoke. There. Now you're safe. Well, okay, sure. In reality, though, you would have to take a step in the x direction. Now you were at the point 0, 0, 0. You took a full step in the x direction. Now let's say you're at the point 1, 0, 0, because you from 0, 0, 0 you went in this vector. You'd have to like recalculate the negative of the gradient again, and then keep changing direction. What you would be doing is called the gradient search method, but you'd be doing it backwards because you would be running not calculating the gradient and going in that direction. You would be calculating the gradient and going negative in that direction a little step, recalculating the gradient and going negative in that direction a little step, and that'll eventually get you to safety after those calculations. Again, same disclaimer as the last video. We talked about lighting a fire in a room. Don't. Anyway, the point of this example, besides like fire, is that you can have gradients of multiple dimensions, of like a 3-dimensional gradient. There could be a 4-dimensional gradient. Now, gradients are also useful for other things. So let's think about this as an idea. Consider a function, a 4-dimensional function, like we had with the smoke here, but I'm taking a level curve of it. So I've got a function of x and y and z, and I'm taking a level curve where the function, the height, the density of smoke, I guess is the way to think about it, is equal to the constant k. If I were to differentiate this with respect to time, this looks like how we derive the gradient. Then I would get the gradient. So let's differentiate with respect to time. Same setup though, right? The same idea as our derivation of the gradient. You would get chain rule, so that would be f, the function differentiated with respect to x, times the derivative of x with respect to some parameter, time we always think, plus the derivative with respect to y times y prime. And in this case, you then get a z derivative, so the derivative of the function with respect to z times z prime. And when I differentiated that constant k, whatever that constant is, its derivative is 0. And this is the gradient vector, the f sub x, f sub y, f sub z, the gradient vector dot product, the tangent vector equals 0. But now we were in 4-dimensional space, but when I take a slice of it, now this is a level curve is an implicitly defined 3D surface. So what's the deal with the gradient? Well, we know it's perpendicular to the level curve. Oh, so it's perpendicular to this level curve. If this level curve is a 3D surface, then this gradient is normal to that surface. It's the normal vector to that surface. So if I think about, if I'm given a function, if I'm given a function and I imagine that the function that I'm given is a level curve of a 4D function. It's in 3D now because I've set it equal to k, but it was a level curve of a 4D function. If I get the gradient of that function, I've got the normal vector to that level curve. What can you do with that normal vector? Well, you can get equation of the tangent plane, because for equation of the tangent plane, all I need is a point and the normal vector. So the tangent plane is given by that normal vector dot product x, y, z without this x and this y and this z are just the general points on the plane. X naught, y naught, z naught are the point about which we're taking the tangent plane. The dot product of those two is equal to 0. Yeah, that's because the gradient and the tangent vectors are perpendicular. But this gives me the equation of the tangent plane. Let's do this as an example. And what about the equation of the normal line? Well, because that's coming up here. Equation of the normal line, what do I need for equation of any line? I need a point, I have that, x naught, y naught, z naught, and a vector. If it's the normal line, then the normal vector is the direction vector of the line. Here I have it written in a symmetric form, but we know we can express it in parametric form or vector form. It's the same two pieces of information. A point that the line goes through, x naught, y naught, z naught, and its direction vector, which in this case is the gradient vector. Let's do an example. So here's our surface. And this is Scientific Workplace drawing it. Let's get DP Graph to draw it. Oh, before we even draw it, and even if we didn't have the picture, let's look at it. X squared minus y squared plus z squared. One negative sign, it's a hyperboloid of one sheet. We can just look at the equation and know what this looks like. Let's draw it anyway, but we already have the picture in our heads. It's a hyperboloid of one sheet. So x squared minus y squared plus z squared equals 1. There it is, as we thought. Take slices in this direction, it's a circle. Take slices in this direction, it's a hyperbola. Slices in this direction, it's a hyperbola. What we want is, we want the tangent plane and the normal line at the point 1, 1, 1. So 1, 1, 1 is about here, let's say. We're talking about it over here. So equation of the tangent plane, the normal line is going to be the line that's perpendicular. They're both the same pieces of information. I need the normal vector and a point. I have the point 1, 1, 1. It's just a matter of get the normal vector. Now, we're going to be thinking of this as a level curve to a 4D function. So in our heads, there's some function, f of x and y, z, that's equal that's what we're thinking, a 4D function. If I take the level curve where it's equal to 1, then this is the shape I get. If I take the level curve where it's equal to 2, then I get a different hyperboloid, a fatter hyperboloid of one sheet. If I take this to be a half, I'm going to get a skinnier hyperboloid of one sheet. If I take this all the way to, let's say, a tenth, let's make 0.01, I'm going to get a super skinny hyperboloid. So these are all nesting inside each other. They're level curves of a 4D function. The particular curve that I'm thinking about, because it's the question, is this one. But that's what I mean about imagining the level curves. It's as if you took, again, we're back to the smoke in the room, and as if I connected all the points together in the room that have the smoke density of 1. That's the shape I would get. Okay, so let's get the gradient of this function. So that's our derivative with respect to x, derivative with respect to y, derivative with respect to z. There's the direction that points in greatest increase, any place along where we're at. But specifically, I mean, where we're at is the point 1, 1, 1. So the gradient in question is that, and that's the normal vector then. If it points in the direction of greatest increase, then it's got to be perpendicular to that, because this is connecting all the places where the smoke is density equal to 1. To increase the density of smoke would be all the way from 1 to 1.1, let's say, and that's a slightly wider hyperboloid of one sheet. So you want to go off the surface perpendicularly to get to that slightly wider one. So anyway, for our purposes though, there's the normal vector to the curve. There's the normal vector to the curve, which is also then the normal vector to the tangent plane. The normal vector is this 2 minus 2, 2. All right, so a plane, a scalar equation of the plane has a ax plus by plus cz equals d. So that would be 2x negative 2y plus 2z is equal to d. And I just need to figure out what the value of d is. Well, the point 1, 1, 1 is supposed to be on there. So when I make x equal to 1 and y equal to 1 and z equal to 1, I'm going to get that d value. So d must be equal to 2. So there's the equation of the tangent plane. Now you could simplify it, divide everything out by 2 if you wanted to, but you don't have to. That's the equation of the tangent plane. We also wanted the equation of the normal line. So the normal line is going to pierce perpendicular through that plane, normal to the plane at the point 1, 1, 1, and normal to the surface as well. What do I need for the equation of a line? A point, got it, and a direction, got it. This normal vector is the direction vector of the line I need. All we have to decide now for the line is, do you want to write it in vector form? Do you want to write it in parametric form? Do you want to write it in symmetric form? Let's write it in vector form, because that's the easiest. So L is equal to the point 1, 1, 1 plus some parameter times the direction vector 2 minus 2, 2. Done. There's the equation of the normal line. There's the scalar equation of the plane. And we use the gradient. If you remember how we did this in previous videos, it was a little bit more complicated without the gradient. So this imagining our 3D surface as a level curve to a 4D shape has given us some more mathematical tools and made answering the question a lot easier.